Welcome to you all to this MOOCs online video course Theory of Yarn Structure. In the last few classes we were discussing about module 8. Today we will complete this module. So far, if you recapitulate what we studied in module 8 is, we first learnt about the mechanics of parallel fiber bundles, especially Hamburger's theory. Hamburger's theory, how it can be applied to yarn, that also we discussed. Afterwards, we studied about the stress strain relation in yarns based on helical model and few other assumptions. We established what will be the coefficient of fiber tensile force utilization in yarn. A special case is Gauss theory, that also we have discussed. We observed a few problems related to Gauss theory. We were trying to solve those problems, and for that reason we learned about the theory of fiber orientation in general fibrous assemblies, and we developed a generalized theory on the tensile behavior of staple fiber yarns. We had a very generalized equation. Then how that generalized equation can be utilized to form Gauss equation, that also we discussed, and then at the end we attempted to partially generalize helical model after incorporation of random character of fiber orientation in yarn, and we developed equations for fiber force, for fiber for yarn force, yarn stress and coefficient of fiber stress utilization in yarn. Today we are going to discuss about the correspondence of those theories with the experimental results. So, before going to the experimental verification of the theories, let us first write down the theories that we are going to compare in this module. So, if you remember, the first one was helical model, and small strain and radius independency. Based on these three concepts, first is the helical model, then the strains levels are small, and then the packing density is constant and also contraction ratio is constant. Based on these three, we derived most general expression for fiber stress utilization in yarn. So, that expression was at a elongation of yarn axial strain tan square beta d, then the integration, this integration starts from 0 to ends at beta d, sigma f, Ef, and then tangent of beta d beta. So, this was our most general expression based on these three ideas. This is the fiber stress utilization phi 2 by this is the fiber stress at yarn strain, tan square beta d is twist angle, this is sigma, sigma subscript f is the fiber stress at an elongation multiplied by tangent of beta d beta. This integral, the limits are from 0 to beta d. So, this equation is a very general one. Let us write it as phi c 1, just for the comparison purpose we use this nomenclature. So, this is the most general one. We have learned in the last class that based on one more assumption, that is your fiber stress strain linear, this equation can be turned into generalized Gekop's theory. So, helical model plus small strain plus radius independency plus fiber stress strain linear. Based on this, we have developed an equation like Gekop. So, we use the subscript g 1 plus eta cos square beta d plus eta logarithmic of cos square beta d by tan square beta d. So, this equation is the result of this concept. Then we have also studied one more equation, very important one, that was because that was the result of partial generalization of helical model. Along with it was small strain plus it was radius independency. Packing density constant and also contraction ratio constant. Based on this, we have obtained a more generalized form. Let us write it as C2. This is equal to 2 by fiber stress at an yarn strain into tan square beta d first integral starts from 0 to beta d, then the another integral starts, that is your 0 to theta u. This all we have already discussed. Ef into cos square theta into u theta into d theta. One integral ends here, and then second one starts, that was your sin beta divided by cos cube beta into d beta, right. So, this we have already derived earlier. So, this is also the result of these assumptions, partial generalization plus small trend plus radius independency. These three equations we wish to compare with experimental results. So, this is the first expression, this is the second expression, and this is the third expression. The associated ideas are also written on the left hand side of those equations, right. So, today we wish to compare these three equations with the experimental results, and we would like to see which of these three equations corresponds mostly to the experimental results. So, for that purpose a study was conducted. In that study, viscose fiber was taken. So, the fiber was viscose, so the viscose fiber was used to produce two sets of yarn, one ring spun yarn and the second rotor spun yarn. Ring spun yarn was of three different counts, 20 ticks, 29.5 ticks and 45 ticks. That was the nominal count. However, after production of yarn the count was measured as 20.07 ticks, 32.45 ticks and 46.78 ticks. The twists of the yarn was also measured, it was 840, 650 and 515. Then the diameter of the yarn was measured 0.169, 0.210, 0.263, and then twist angle was also measured 23 degree, 21 degree, 22 degree. So, ring yarn of three different counts were produced. Similarly, rotor yarns of also three different counts were produced. The counts were, nominal counts were 20 ticks, 29.5 ticks and 50 ticks. After production of those yarns, the counts of the yarn were measured as 20.03 ticks, 30.71 ticks and 52.15 ticks. Also the twist of the yarn was measured, diameter of the yarn was measured, twist angle was measured. These results are given here. Now, those yarns were also tested for fiber stress strain curve. Now, so the viscose fibers were also tested for stress strain curve, also these yarns were also tested for stress strain curve. Now, viscose fibers had linear density 1.3 decitex and length was 38 mm. So, this fiber was tested for stress strain curve, and we have kept the gauge length at 10 mm. So, while obtaining the stress strain curve of the fiber, the gauge length was kept at 10 mm and test speed was kept at 10 millimeter per minute, right. But for yarn those test parameters were a little different. So, for yarns the standard gauge length is at 500 millimeter and test speed was kept at 110 millimeter per minute. Right. Now, when we measured these fibers, approximately 100 fibers was tested. Now, as fiber stress, fiber strain all are random variables. So, obviously these 100 fibers, though they are from viscose, however, there was little variation in stress and strain of these 100 fibers. So, what we did, we have taken the average stress strain curve of the fiber. How did I do that? Now, for actually we used linear interpolation technique and stepwise, say for 0.01% of strains, we applied linear interpolation technique to obtain the average stress strain curve of the fiber, right. Similarly, for yarn also, on each yarn 100 yarns were tested. So, there were 3 ring yarns and 3 rotor yarns. So, in total 600 tests were carried out. Now, when on one yarn we carried out 100 tests, again being random variable, the yarn stress, yarn strain were different. So, we obtain average yarn stress strain curve by using same linear interpolation technique for an interval of 0.01% strain level. So, we obtained the average stress strain curves for fibers and for these 6 yarns. I will now show you the results. So, this is the experimental stress strain diagram of fibers and yarns. The top curve is for fiber, then bottom there are 6 curves, these first 3 for ring yarn and the bottom 3 are for rotor yarn. So, for 3 different counts, here also for 3 different counts you see the curves. Along the x axis fiber strain as well as yarn strain are plotted. Along the y axis fiber stress as well as yarn stress in unit Newton per tex are plotted. Now, if you remember, in the last class we showed you schematic stress strain diagram of fiber and yarn. Here it is actual stress strain diagram of fiber and yarn. They are very similar in the sense fiber stress strain curve is lying over the yarn stress strain curve. Though both are looking very similar, however, these points, generally speaking, fiber breaking strain is higher than the yarn breaking strain, and also fiber breaking stress is higher than the yarn breaking stress. And what more we can see from this graph is obviously ring yarns are exhibiting better tensile characteristics than the rotary yarns. Well, further we can observe that this distance, say at given fiber or yarn strain, the difference between fiber stress and yarn stress, this difference is not same for different levels of strains. What I mean to say is that this this difference is not same throughout these two curves. Similarly, for rotary yarns also this difference, the difference between fiber stress and yarn stress is not same for different levels of fiber or yarn strain. However, as you know, Gegoff theory exhibits constant fiber stress utilization, but experimentally we can observe here that it is not same for different levels of strain. Right. So, now using these diagrams we obtained the coefficient of fiber stress utilization by yarns at different levels of strains. So, first we will discuss about ring yarns, then we will discuss about the rotary yarns. For the ring yarns, different levels of strain, this difference we calculated and we obtained the curve for fiber stress utilization in yarn for different levels of strain, and this we have done for 3 different counts: 20 ticks, 29.5 ticks and 40 ticks. Let us show you the result. This is the result. This is for 20 ticks, this is for 29.5 ticks and this is for 45 ticks. Ring yarn. Along the x axis for all these 3 graphs, strain, yarn strain is plotted, and along the y axis coefficient of fiber stress utilization in yarn is plotted, phi, lowercase phi. Now, phi subscript e stands for the experimental data. So, for 20 ticks this is the behavior of phi subscript e. For 29.5 ticks, this one is the phi subscript e, and for 45 ticks this is the phi subscript e, experimental fiber stress utilization. Then, as I told you earlier, we used to compare with these three equations. Phi subscript g is very similar to Gegop's equation. Precisely speaking, this is not Gegop's equation because Gegop's considered eta 0. So, if in the right hand side only cos square beta d term is there, then it is Gegop's equation. However, let us think that this is Gegop's and other type of equation, and this is the one expression, this is the second expression. This is phi subscript C1 and this is partial generalization phi subscript C2. So, first let us talk about Gegop's equation. As you understand, because of the fiber stress strain relation is linear, Gegop's equation always gives you the same values for different levels of strain. This is the Gegop's equation for 20 ticks, this is for 29.5 and this is for 45. This curve, this straight line parallel to x axis, right. Then comes your the first one, helical model, small strain and radius independency, phi subscript C1. This equation was solved. So, using suitable numerical technique, phi subscript C1, this one, here it is this, see it is always higher for all three yarns, right. And partial generalization of helical model, that is your phi subscript C2. This was also solved using the same numerical integration technique, and we obtained this curve, this one and this one. Right. So, what we see here that phi subscript C2 is very close to the experimental result, right. And for this phi subscript C2, the value of C was considered, so was considered to be 4.9 and eta was considered to be 0.5, right. So, the partial generalization of the helical model exhibits very close correspondence with the experimental results. If you notice carefully in these graphs, there is one more thin line is present. Say in this one, in between phi subscript E and phi subscript C2, there is a very thin line is present. Similarly, very near to phi subscript C2, this thin line is present in this graph, and here also very near to phi subscript C2, a thin line is present. This thin line was obtained by multiplying a factor to phi subscript C1, so that the phi subscript C1 comes down. So, that factor for this case was 9. This was purely empirical basis. So, it was of interest to see if we multiply by some factor to phi subscript C1, whether it gives very close correspondence or not, and it gave. You can see this line is very thin line is very close to experimental results. So, that was basically just to empirically it was the reason. Now, an obvious question is now arising. It is quite clear that phi subscript C2 is very close to experimental results, and when we multiply by some parameter phi factor k 0.79 to phi C1, then also it gives very close results. However, phi subscript C1 is always staying above, much above the experimental results. The obvious question is, why is it so? Why does phi subscript C1 stay much above than the experimental phi subscript E curve? In all three yarns we see similar tendency, that means there is some reason. This trend is not random, there must be some reason for this. What is that reason? That is the question. Now, if you go back, the answer, the hint of the answer is here in this slide, in this paper. Phi subscript C1 is based on pure helical model. In pure helical model, the fiber configuration is perfect. However, in reality, in actual yarn, fibers are not so perfectly organized in the yarn. That is the reason why the actual curve is staying bottom than the phi C1 curve. So, in all cases we see, when we multiply by a factor 0.79, that probably corresponds to this perfect imperfect fiber organization, we see there is a very close tendency between the experimental and case multiplied by phi C1 curves. So, this is our observation from this. What message we are taking? The message is that the partial generalization of helical model along with the two more assumptions, that is small strains and radius independency, packing density constant, contraction ratio constant. These all assumptions together with the partial generalization of helical model yields very good correspondence with the experimental results for the ring yarn. Whether the same is true for rotary yarn, let us try to see what happens to rotary yarn. So, now we will discuss for rotary yarn. So, this is for rotary yarn. 3 different counts, 20 ticks, 29.5 ticks and 50 ticks. Similarly, the experimental phi subscript E is this one here for this yarn. For this yarn it is here, and for this yarn it is here. Gegop's equation for this yarn here, for this yarn here, for this it is here, and phi subscript C1, this is here, this is here, this is here. What about phi subscript C2? It is here for this yarn, it is here for this yarn and it is here for this yarn. Now, here again we did the same procedure, we multiplied phi C1 by a factor. In this case, this factor was 0.55 and what was the value of C? The value of C was 1.6 and the value of eta was same 0.5. Now, what we see here? Here again phi C2, that is related to the partial generalization of helical model, gives very close correspondence with the experimental results in all three cases. Gagop's model as usual stays much above than the experimental curve, and phi C1 helical model stays further above than Gagop's one and also the experimental one. When we multiply by this factor 0.55 to this phi C1, it gives a very close correspondence. The thin lines present in between phi C2 and experimental basically corresponds to the curve which is obtained by multiplying 0.55 to phi C1. Here again we see that partial generalization of the helical model results into very close correspondence with the experimental results. Now, if you look the value C 1.6, what is C? Measure of anisotropy. C is equal to 1 means isotropic. As the anisotropic increases, the value of C increases. For ring yarn it was 4.9, much higher than 1.6. So, the anisotropy level in ring yarn is much more higher than the anisotropy level in the rotary yarn, because of the fiber configuration. In rotary yarn usually belts are formed. So, and also there are significant fiber disorders present in rotary yarn. As a result, the value of C is less in case of rotary yarn than ring yarn. Poisson's ratio or the contraction ratio was considered to be same 0.5. However, the value of K 0.55. This was probably associated with the more disordered character of fibers in rotary yarn. So, and also it is well known that rotary yarn deviates much more than from the helical model. So, what message we obtain from this is that the partial generalization of helical model along with the assumption of small strain and radius independency lead to better correspondence with the experimental results. So, you can see that in real yarn the tensile behavior corresponds very well to the model of partial generalization to helical model. So, this ends module 8. If I summarize module 8, then we in this module, the first class we started with mechanics of parallel fiber bundle. There we also discussed what will be the mechanics of blended fiber bundle, especially Hamburger's theory we discussed. How Hamburger's theory can be applied to yarns, we gave a very small note there. Then we solved a few numerical problems before we proceeded to the stress strain relation in yarn. In stress strain relation in yarn, we first established the relation between fiber strain and yarn strain. Then we derived the expression for yarn stress and also the expression for coefficient of fiber stress utilization in yarn. In that expression, when we considered contraction ratio 0, it turned out to Gagop's equation. Then we discussed a few numerical problems associated with Gagop's equation. Then we introduced a problem with Gagop's equation. The problem is Gagop's equation gives same value for fiber stress utilization for different levels of strain, which is not experimentally correct. So, we were trying to find out the reasons. We studied two mathematical models. One was associated with helical model, generalization of helical model. One was associated with the helical model, second was associated with the partial generalization of helical model. In order to understand that, we had to understand fiber orientation. So, we discussed about theory of fiber orientation and we solved a few numerical problems. Then we studied general tensile behavior of staple fiber yarn. There we started with tensile behavior according to helical model. We established generalized equation. Then we showed you how this generalized equation can be turned to Gagop's equation. Then we partially generalized helical model. We brought the random character of fiber orientation into account and we developed expressions for yarn force, yarn stress and coefficient of fiber stress utilization in yarn. And then today we compared those theories with experimental results for ring yarns as well as for rotary yarns, and we found in both the yarns the partial generalization of helical model gives very good correspondence with the experimental results. So, these are all we discussed in module 8. So, module 8 ends here. Thank you for your attention.